Okay, so let's get started with the doubt sheets. Someone has found a typo in the online notes. Thank you very much. I wrote grad x instead of delta x, which we wrote correctly during class yesterday, but in the online notes it's grad x. Anyone wants to claim this? No one? Okay. So I had a prof in not undergrad in during my PhD time. He was a Canadian prof, and back then to do our laundry we had to use a coin operated machine, right? So every time anyone would answer a correct question, he would throw a quarter to us, and we would use that quarter for doing laundry, but I don't have any quarters for them. There's a question, can we apply chain rule of differentiation to inner products? I think the student was sitting right at the center last time. That was you. Yeah, so what you have written is, let me just write that down. So the question is, can we do something like this, x transpose Ax, and he's written that as Ax. This is another way of writing an inner product, but the first step is kind of illegal when you do this. You said d of Ax, x plus Ax dx, which looks okay, but then the next step is you cannot move this d like this. What you've written is a times dx. Now, because a into x scrambles up all the x's, you cannot move the derivative operator straight away inside here, although you finally get the correct answer by doing this. But this operation is illegal. But you could come up with some equivalent way of writing it. But in our case, this is already an inner product, so we don't have to write it separately like that, right? What are the applications of Jacobian operation? Does it explain the relation between input and output variable? So we saw that what was actually Jacobian expressing? Derivative, but a little bit more. If you were to write it in plain English, what is the Jacobian expressing? Rate of change of each of the component functions with respect to each of the variables, right? So it's not exactly input output. It's a better word would be sensitivity of each function to each variable. Okay. We wrote the definition of the directional derivative for a scalar function f of x, and the question is, can we generalize it to a multivariable function? Yes, just go component wise. Okay, multivariable calculus seems to be interesting, but also huge. I guess I need little practice to get a good grasp. Can you provide some materials for practice? Has everyone seen this YouTube channel 3 Blue 1 Brown? Right. So do they have stuff on multivariable calculus, or is it only linear algebra? I've seen linear algebra. I don't think I've seen multivariable calculus. But if anyone, this is open to everyone. Those of you who have not seen 3 Blue 1 Brown, please go and have a look at it. It's a great tool for linear algebra. And if someone finds a similar tool for calculus, that would be great. I don't know of a tool myself. One video? Oh, okay. Nothing for multivariable. Okay, then this was Jaikar. Is Jaikar here? Not here. Okay. Question was about the definition of grad f, and can you go both ways? It's not a if and only if statement that I have to go both ways, just a definition, so need not sweat it. Okay. Right, so today's lecture we will finally get into proper optimization, unconstrained optimization, right? The first half of the course, which is unconstrained, the second half is constrained. So let's begin with unconstrained. Okay. So let me just give you a bit of an overview of what we will cover in this module. This is roughly chapter 2 of Nosedal and Wright. Okay. If you want to read the full textbook, you can read chapter 2, or you can read the online notes. Okay. So when we're talking about unconstrained optimization or optimization in general, we could be talking about maximizing a function or minimizing a function. To avoid confusion, in general, I'm going to talk about minimizing a function. If you have a maximization problem, all you need to do is multiply by -1, it becomes a minimization problem. Okay. So leaving aside all technical details, what is the nature of the game? Find a minima, right? So never lose sight of that. That's what we're trying to do, right? So that's the bottom line. Now, the moment I write this, there's a little bit of ambiguity over here because a problem can have multiple minima, right? So I should qualify this. I should say identify a local minima. Okay, that's what I want to do. I want to identify a local minima. Okay. In general, finding a global minima can be very challenging. We'll talk about it as we go, but something simpler is to identify a local minima. So what do I mean by identify? Some kind of a test that if I get a point, how do I verify that, is it a candidate for a local minima? So we want to look at tests for this. Okay. And we have basically, we're going to talk about two different types of tests depending on how differentiable the function is. So the building block for this is multivariate Taylor's theorem. Okay, so if we're going to use Taylor's theorem, and depending on how differentiable the function is, I'm going to either be able to use first order or second order, let's call them conditions. Conditions for what? Conditions to identify the local minimum. Okay. From here, we will sort of go to an overview of algorithms. Okay. Again, in the world of algorithms, broadly there are two classes. One is what is called a line search. The other is called a trust region. Two different approaches for solving optimization problems. Okay. In this course, we are primarily going to talk about line search algorithms. Okay, that itself is an extremely vast subject. Okay. So this is just sort of the roadmap. Okay, so our theme now is identifying. That's the first thing I want to do. Now, to give a special word for this local minima, I'm going to write it as x with a star on it. So if you see x star, in general, it denotes this point, which is a local minima. Okay, and because I've already given you a hint that there may be multiple minimas, there must be some hierarchy of minimas, right? So the hierarchies are local minima, and the best of all minimas, what would you call it? Global minima, right? So the global minimizer obviously f of x star is less than equal to f of x, right? And what should I say about x? For all x in the domain of f. This is the natural definition of the global minimizer. Then you come to the local minimizer. Okay. Obviously, this statement would be the same. F of x star is less than equal to f of x, but now x belongs to some set or neighborhood of some point. Okay. You will find in the literature when people talk about minimizers, they add one more adjective. They may not just call it a minimizer. They may call it a weak minimizer or a strong minimizer. Okay, so these are the adjectives. These words are fairly self-explanatory. So if you were in charge of definitions, weak would mean what? Okay. Okay, what would be a strong minima? Okay, so it's a little different. If you see less than equal to, it's a weak minimizer. If you see, it's a strong minimizer. So I can have a weak global minimizer, I can have a strong global minimizer, right? And the best way to see it is, let me plot for you. This is, let's say, x, this is f, right? And I have a function that comes like this and goes like this, right? Now this point over here, x star, is clearly a strong minimizer. It's a strong global minimizer. I could also have something like this where it comes over here, right? Now I have these all points on the same line are all minimizers. So they are weak minimizers because that equality is being satisfied, and you can have both that are happening. So this greater than, I mean less than equal to or less than can make a difference. Okay. So these subtle points can become hard to verify in multiple dimensions, right? So we have to, usually we are kind of careless about less than equal to or less than, but this can make a big difference. So if different people are solving the same problem from different starting points and they end up with different solutions, that's possible, right? One guy started and ended up here, another guy started and ended up here. They're all correct, right? Now, what we'll see is that in the whole game of optimization, particularly when we're talking about non-linear optimization, your starting point becomes important. Where you start often determines where you end. So that's why you can start from some point over here and maybe end up here, or you could start from here and end up over here, right? That's why it's important to know whether it's weak or strong. Now here is the point at which convex optimization and non-convex optimization differs. This is one of the great simplifications in convex optimization. Does anyone want to guess? Correct. So in the case of convex optimization, if you find a local minimizer, it is the global minimizer. So you don't have, if you find one minimizer, you're done. The problem is over in the case of a convex function, right? So convex functions, if I have a convex functions, then any local minimizer is also a so this is a very important result, which also tells you that optimization in general, if the function is not convex, can be very, very challenging, right? So I mean, if you want to see an illustration of that in one dimension, that simply means this. Supposing I have a function x, so a convex function will look something like this. That's how we've already spoken about what a convex function looks like. So therefore, if I find this, it's a local and a global minimizer both, right? I'm done, the problem is over, right? On the other hand, if my function looks a little bit like this, right? Now the kind of techniques that we will do, they all are kind of local optimization techniques. If you give me a starting point, I'm going to travel in by using some recipe and reach a minimizer. So if I started from here, from this value of x, that is on this value of f, I will land up here. If I start from, let's say, here, I will land up over here. On the other hand, if I start from here, I end up over here, right? Right. So this entire course is going to be about local optimization problems, because those can be written mathematically using the language of calculus and so on. If you wanted an algorithm that would give you the global minima overall, right, that's a totally different family of algorithms, genetic algorithms, evolutionary algorithms, simulated annealing, all of these things. for which there is the mathematical analysis is not as well developed, okay, and it's kind of a little bit like black magic. Also computationally very heavy. You cannot do it for large variables, large number of variables, okay. There is something called, many of you might be familiar with this phrase, the curse of dimensionality. As the number of dimensions increases, it becomes harder and harder for you to solve the problem. Okay, so this is what makes convex functions special. Any questions so far? Okay, so let's come to perhaps the most useful theorem in this course, which is Taylor's theorem. You've all seen Taylor's theorem in class 12 for scalar variables, scalar functions. Now we are going to generalize it without proof for the multivariable case. Proof is actually not that straightforward. So links are there on the online notes for you to have a look at it, but I'm going to only state it. And I'm going to make life simple and start with a scalar function of multiple variables. So Rn to R is what my f does. Okay, common notation is that I'm going to talk about 2 points which live in n-dimensional space, and I will work with a scalar which is so now what I'm going to do is I'm going to give you 2 flavors of Taylor's theorem. One is to first order and the second is to second order, right? If your function is nice and well behaved that you can define a second derivative, or in this case a Hessian, then you will write it to second order. If it turns out that your function does not have a second derivative, then you have to stop at the first order, right? So I will state both of these possibilities of the function. So first, let's say continuously differentiable. So i.e., I'm going to call this first order, okay. So Taylor's theorem is going to help me write down the value of the function at a point x plus p in terms of f of x and grad f. That's, I mean, what you are expecting. So f of x right. This is technically, what is this theorem? This is the mean value theorem, because x plus tp is a some point between x and x plus p, right? And this is equality, this is exact, okay. Now if I have a twice continuously so this is i.e. second order, I just need to add one more term. This time it's the derivative at x, not x plus anything. And then the second term, there comes a half p transpose Hessian at x plus dp, and okay. So I'm stating this without proof, but this is following straight. I mean, the expression looks just like the expression for the scalar function case. Okay. Now there are simple ways in which you can interpret this statement. You are all familiar with Taylor series, right? I write a Taylor series of a function up to nth order, and then whatever is left is the error term, right? So you could interpret this as, for example, this is Taylor series up to what order? First order, and then this is a error term, you can call it like that, or error or remainder term. Right, and you're familiar, I drew this last time, but I'll draw it once again. You're familiar with the geometry, right? This is my point x, this is, let us say, my vector p. So therefore this vector addition gives me the point x plus p, Now t is a scalar going from 0 to 1. So as t goes from 0 to 1, x plus tp is here. This is my x plus t into p, right. So the function value at this point b, starting from the function value at this point a, and some derivatives along the way. That's how you can interpret this. Okay. So this is, I mean, just information at this point. There's nothing that we have derived. Okay. Before I state the first order and second order conditions to identify the local minima, there is one more definition which you should become familiar with, because you'll come across it everywhere in the textbooks. It is something which is called a open neighborhood of a point. Okay, so let's just make a note of that. Open neighborhood of a point. Okay. The word open should be a hint to you. It's essentially the generalization of an open set. So if this is my point x star, neighborhood means I define some small ball and carve the space around this x star, but I don't include the boundary. Okay, then this region is called an open neighborhood about the point x star. Okay, so if I were to write it in terms of norms, how would I write it? So let's say this radius is epsilon, is less than epsilon, not less than equal to.